The James Webb Space Telescope, JWST, stands as the premier global observatory in astronomical research. Its chief objective is to probe the enigmas surrounding both our own planetary system and distant exoplanets orbiting far-off stars, as well as to examine the intricate structures that constitute our cosmos and our position within it. In a groundbreaking endeavor, scientists recently directed the JWST toward a star situated 120 light-years from our solar system. In doing so, the formidable telescope has uncovered compelling evidence suggesting the presence of carbon-based molecules in the atmosphere of a potential ocean world far beyond Earth, which has left the astronomical community astounded. But how is this extraordinary discovery feasible? This revelation offers an intriguing glimpse into a planet that stands in stark contrast to any found within our solar system, while also raising thought-provoking questions about the potential for habitable worlds elsewhere in the vast expanse of space. Join us as we delve deeper into this discovery of an exoplanet and uncover the fascinating details it holds. If you're eager to stay informed about the latest revelations concerning the universe and beyond, be sure to subscribe to our channel, like the video, share it with others, and activate the notification bell to stay up to date. NASA's James Webb Space Telescope has made a significant discovery regarding the exoplanet K2-18b, a planet that is 8.6 times more massive than Earth. What makes this image so exceptional? This thrilling finding includes the identification of carbon compounds such as methane and carbon dioxide in its atmosphere. The telescope's detection adds weight to earlier research suggesting that K2-18b might have conditions favorable for life. It appears to possess a hydrogen-rich atmosphere and a surface enveloped by oceans. The initial analysis of this exoplanet's atmospheric properties situated within the habitable zone was conducted using NASA's Hubble Space Telescope, which dramatically enhanced our understanding of the system. It's crucial to note that K2-18b resides 120 light-years from Earth, located within the constellation Leo, and orbits a cool dwarf star known as K2-18. This star lies within the habitable zone of its system. Exoplanets K2-18b, which fall between the sizes of Earth and Neptune, are a rare category in our solar system due to the absence of similar planets in our immediate vicinity. The possibility that K2-18b harbors a significant amount of carbon and a hydrogen-dominated atmosphere is intriguing to astronomers. Many experts believe such planets may offer ideal conditions for the search for signs of life. The presence of methane and carbon dioxide, along with the absence of ammonia, strengthens the hypothesis that this exoplanet might contain an ocean beneath the hydrogen-rich atmosphere. Early research has also suggested that dimethyl sulfide, the chemical compound produced by life on Earth, might be detected in K2-18b's atmosphere on Earth. Most dimethyl sulfide is generated by marine plankton, but the evidence for this compound on K2-18b remains weak and requires additional confirmation. Further observations using the JWST telescope network should help determine if dimethyl sulfide is indeed present in the atmosphere of K2-18b in significant amounts. One astronomer from the University of Cambridge clarified that K2-18b lies within the habitable zone and contains carbon compounds. It does not automatically imply that life can exist there. The planet's radius, which is 2.6 times that of Earth, suggests that its core might be surrounded by a thick, high-pressure mantle of ice similar to Neptune's. Additionally, it has a thinner, hydrogen-rich atmosphere, and its surface is ocean-covered. Although liquid water oceans are anticipated on this exoplanet, there remains the possibility that these oceans may be too rigid or inadequate to support life. However, researchers have succeeded in obtaining the most detailed spectrum of a habitable subtoon planet, to date enabling them to identify the molecules present in its atmosphere. Member of the Cardiff University team explained that this challenge was met by analyzing light from K2-18b's host star as it passed through the planet's atmosphere. K2-18b is classified as a transiting exoplanet, meaning its brightness diminishes when it crosses in front of its host star. This is how NASA's K2 mission first identified this exoplanet. During these transits, a portion of sunlight passes through an exoplanet's atmosphere before reaching space. Telescopes like JWST as sunlight filters through an exoplanet's atmosphere. It leaves behind signals that astronomers can use to identify the gases present. The research team intends to conduct additional investigations using JWST's mid-infrared spectrometer to confirm their findings and gather further data. K2-18b's climatic conditions. The team's ultimate goal is to search for signs of life on habitable exoplanets, a breakthrough that could revolutionize our understanding of the universe. Furthermore, the JWST has made other extraordinary discoveries. Astronomers using the telescope have detected complex organic molecules akin to smog or smoke in a distant galaxy. This discovery marks the earliest known detection of such molecules in the universe. Personally, I find this both awe-inspiring and unsettling, as these findings in the farthest reaches of the cosmos are reshaping the very foundations of our cosmology. The importance of this discovery lies in the fact that these molecules, known as aromatic hydrocarbons, were found in a galaxy that formed when the universe was only about 10% of its current age. These carbon-based molecules, which are found in petroleum and coal deposits on Earth, as well as in atmospheric pollution like smog, are large and complex, composed of dozens or even hundreds of atoms. What makes this discovery so remarkable is that such large and complex molecules were formed so quickly after the Big Bang, defying expectations based on our existing cosmological models. To put this in perspective, the light detected from this early galaxy started its journey less than 1.5 billion years after the Big Bang, whereas the universe is about 13.8 billion years old today. This means we are witnessing some of the first steps in the universe's evolution. What is most impressive is that the detection of these complex organic molecules was made possible by the Webb telescope, which will continue to allow us to make similar observations for nearly a billion more years. If we could observe even further back in time, would we be able to find even more of the molecules, perhaps closer to the Big Bang itself? This raises profound questions about our science and our understanding of cosmology. Until now, previous attempts to detect complex organic molecules in ancient galaxies could only confirm their presence, but with Webb's higher resolution, we can now examine the fine details of where these molecules are located. Additionally, the uneven distribution of these molecules in the early galaxy SP4-1847 remains an unsolved mystery. What's truly impressive is that this galaxy was already as massive as our own, with stars that had generated as much carbon and oxygen as those in the Milky Way, despite being only 1/10 the age of our galaxy. As humanity ventures deeper into the unknown, armed with knowledge and insight, we are humbled by the vastness and complexity of the cosmos. With every scientific breakthrough, we move closer to unveiling the enigmas concealed within the stars. As our global space exploration network progresses, it's merely a matter of time before the cosmos discloses even more of its hidden truths, shining ever more brightly in the process. Please share your reflections in the comments section. If you found this video engaging, don't forget to subscribe and activate the notification bell, as our comprehension of the universe advances the James Webb Space Telescope consistently delivers. Transformative insights. Its observations are reshaping how we view exoplanets and celestial formations, extending the limits of what we previously thought possible in astrophysics. This extraordinary observatory enables us to peer farther into the universe than ever before, unraveling secrets that have long puzzled scientists. The identification of complex organic compounds in remote galaxies serves as just one instance of how JWST is redefining our perception of the cosmos's early history and its continual development. One of the most captivating elements of these findings is the potential that life, or at least its foundational components, might be present in regions once considered inhospitable. The detection of carbon-containing chemicals in the atmospheres of distant planets like K2-18b introduces new paths for examining possible biosignatures on planets that bear some resemblance to Earth. Compounds such as methane and carbon dioxide, commonly linked with biological processes here on Earth, are noteworthy. However, their presence alone on distant worlds doesn't guarantee life exists. Instead, they encourage further exploration into the environmental conditions that could support life elsewhere in the universe. NASA's future strategies for exoplanet studies are focused on this very potential. The Webb telescope's capability to scrutinize exoplanet atmospheres with such unprecedented precision represents a major stride forward. It allows scientists not only to detect fundamental elements but also to identify intricate molecules that may signal biological activity. This level of accuracy is vital for evaluating the possible habitability of distant planets. As our expertise deepens, so does our potential to spot subtle indicators of life, whether they be atmospheric gases, organic substances, or other biomarkers that may imply the presence of living organisms. Beyond its achievements in exoplanet research, the JWST is also delivering invaluable data about galaxy formation and transformation. By observing faraway galaxies, astronomers can map the chronology of star creation, track the distribution of elements, and uncover the mechanisms that shape galaxy growth. These investigations are essential for deciphering the origin of our own Milky Way galaxy and understanding its progression over cosmic time. The discovery of aromatic hydrocarbons in a galaxy that formed so early in the universe's existence adds another crucial piece to this cosmic puzzle. It suggests that the chemistry necessary for life may have emerged far earlier than previously assumed. This implies that the basic materials for life could have been widespread throughout much of the universe's timeline, increasing the chances that life could exist or could have existed elsewhere. As we continue to push the frontiers of exploration with the James Webb Space Telescope and other state-of-the-art instruments, we find ourselves in a new epoch of discovery. This new era is defined by our enhanced ability to examine the universe with greater precision and depth than ever before, empowering us to pose and begin to resolve some of the most profound questions regarding our existence and role in the cosmos. So what are your thoughts on the recent revelations made possible by the James Webb Space Telescope? Do you think we're nearing a historic moment of discovering life beyond Earth, or are we merely uncovering the elemental pieces that may one day lead us to that extraordinary finding? Let us know your thoughts in the comments, and remember to like, subscribe, and stay tuned for more astonishing updates from the cutting edge of space exploration.